Hi guys, in this video we're going to continue our discussion about copulas, and we're really going to have a deep dive into the topic. So the first video was more of a general introduction, explaining the concepts, giving intuition and the overall theoretical framework. In this video we're really going to go into the small details, and the way it's structured, it's more with a practical mindset. So this video is more code driven. There's an R code that we are going to follow. But before each segment, I'm going to show you the necessary theory in the slides, and so we'll switch back and forth. And here's an outline of what we're going to do in this lecture. We're going to draw 2D contour lines of copulas. We're going to generate data or sample from copulas, and we're going to fit copulas to synthetic data that we've generated. And we're going to first focus on 2 dimensions, but then move to higher dimensions. And in higher dimensions, we're also going to look at simple or traditional copulas, which I skipped over in the previous video. So we'll start with the bivariate logistic example from the previous video. Here you can see the copula CDF that we found. And if we take the double derivative of this, we get the copula PDF. So let's switch into R and see how we can draw contour lines of these two functions. So to kick things off, we're first gonna load the tidyverse library, and also ggdark because I prefer dark plots. And now here we have the copula function written as a code, and here the density copula. And we're gonna create a grid, and we're gonna, for each point in the grid, evaluate the value of the capital C and lower c functions, the copula and the density. And then we're gonna plot the contour lines of the CDF, you can see it here, and of the PDF, which looks like this. Now, one thing you might have noticed, I've started the values at 0.05. The reason being is that as U1 and U2 approaches 0, the copula density approaches infinity. And so in order for this graph to actually look more than just purple with a bright dot here, I've started it from 0.05. So we know how to draw contour lines, but what about sampling from these distributions? I want to show you 2 methods to do so. So the first method is rather easy. We sample from a joint distribution, some known joint distribution, that has an underlying copula structure. And then we simply convert the samples using the marginal CDF functions. That is, we take each dimension, the x and the y, or x1 and x2, and we transform it using the CDF of the marginal. So now our samples are in the U space and we have samples from a copula. After that, we can apply any inverse CDF or quantile function to the marginals and get a new distribution that has that core structure, that underlying copula structure. Now the problem with this method is that we rely on dependent structures that are coming from known joint distributions. So the second method is to sample directly from the copula. And there are several ways to do this. We can use the conditional inversion trick, but there are also other approaches. For example, as we shall see later in this video, for Archimedean copulas, we have the Marshall-Olkin approach. And in harder cases, we can use general purpose sampling, like for example, Monte Carlo methods. In any case, once we have these samples, we can again decide on their marginals and transform them accordingly. I will show the second method on our Bi-Logistic example and the first method on the Gaussian Copula. So let me explain the second method, and specifically the conditional inversion. The idea comes from the factorization property of probabilities, so the probability of x and y is equal to the probability of x times the conditional probability of y given x. So what we can do is sample from the marginal p of x, and then sample y from the conditionals given the x's that we've already sampled. In our copula space, the marginal is simply the standard uniform. So all we need to do is sample from the conditional. How do we do that? Well, first, let's find the conditional form analytically. Then we'll use the inverse transform sampling to sample from it. So if you've never heard of inverse transform sampling, let me quickly explain it. Suppose our distribution is the exponential, then we can find the inverse CDF or quantile function, and this is equal to this. What we do is sample from uniform distribution and transform the results using the quantile function. And if we check what the CDF of this transformation is, we get it's equal to the CDF of an exponential distribution. And so our x's are distributed exponentially, because the CDF completely and uniquely define the distribution. Now let's find the conditional of the copula. The conditional of the copula is simply the partial derivative of the copula with regards to the conditioned value. We first calculate the partial derivative to get this function, which also for ease of notation is called the h function. And now in order to sample from this conditional, we invert it using inverse transform sampling. We generate random v's from a standard uniform, and so now in this equation, both u1 and v are known, and we solve to get u2. Let's also establish some nomenclature. u1, let's call it the conditioned value, and v, let's call it the target value. And you'll see later down the road when we have a 3-dimension example why this is necessary. Okay, so for the sampling, I implemented here the code that basically does what I've shown you on the slide. It takes u1 from a random uniform, it takes v from a random uniform, it inverts the conditional using the v's and the u1, and so to get u2. And here I sample from this function and I plot both the samples and the contour lines based on these samples. And we can see the samples here, and we can see also indeed the empirical contour lines resemble the theoretical PDF that we've derived before. What about cases like the Gaussian, where we can't write the CDF analytically? This means that we can't actually write the copula analytically either, but it shouldn't stop us. So in the last video, I showed you that we can write the joint CDF as the copula function of the marginal CDFs, but we can also write it reversely. We can write the copula function as the joint CDF of the quantile functions. And it turns out that this is equal, in the Gaussian case, to the standard normal marginals and the joint of a bivariate normal with means 0, standard deviations equal 1, and correlation of rho. This also kind of makes intuitive sense because we only care about the dependent structure. We don't care about the marginals, mean, or standard deviation, the location or scale. We don't care about them. All we care is the actual dependent structure. So once we'll develop it, we'll see that they can go away. And in case you don't believe me, you can check the derivation here to see that indeed everything works out and the location and scale information is not crucial. What about the PDF? Well, we can use the identity we found in the last video given by this equation over here. So the copula is equal to this, and plugging in the equation from the last slide, we see that we can use the standard normal PDFs. Note that I'm using x's here for brevity to denote the quantile values. If we plug everything together, we'll get this expression. We can also write this in matrix form, which is how Wikipedia writes it, where R is the correlation matrix. So for drawing contour lines, we simply create a grid and transform the points accordingly. For sampling, we sample from the bivariate normal and transform using the standard normal marginals. For Gaussian Copula, we're going to use the MVT norm package for sampling from multivariate Gaussian. What we have here is the way to evaluate the CDF of the Gaussian Copula. We use the inverse of the standard normal of u1 and u2, and then we plug it into a bivariate normal distribution with mean 0, 0, and a covariance matrix, a sigma, equal to 1, rho, rho, and 1, as we saw in the slides. And for the density, we use the joint divided by the marginals. Again, we transformed variables using the marginals. We calculate the numerator, then the denominator, and we divide both of them. And again, I'm creating a grid, calculating both values. Let's run this. And now let's plot the CDF. Okay, so it's a bit different from the CDF of the bivariate logistic. You might not see it. You can go back. Or maybe I'll put, in post-editing, I'll put the image of the bivariate logistic. Yeah. Let's see the PDF. Here you can see it's quite different, yeah? So here, this and this looks very symmetric. So we have a peak here and a peak here, whereas in the Bi-Logistic example, we only had a peak here and a much less rise in this corner. To sample from a bivariate Gaussian is quite simple. We just sample from a bivariate Gaussian and then transform the points using the marginals. So again, I'm sampling from this, plotting both the points themselves and the empirical contour lines. Again, we see that the empirical contour lines really resemble the theoretical PDF. So what about fitting to data? In the last video, I mentioned that we tried different Copula families, find their best parameters, for example, using maximum likelihood, and then compare them using some criteria, for example, the AIC. Let's do this in R, both manually and using the Copula library. The Copula library can also automatically do most of what we've done so far, that is, compute densities, sample, and adding arbitrary marginals. Okay, so to fit the data manually, I'm gonna have these few functions here. The first one is computing the log likelihood of the Bi-Logistic. It's just taking the log of the logistic PDF and summing it. Here I have for the independence Copula. Well, the independence Copula we already saw. Its CDF is equal to u times v, and if we take the double derivative, it's equal to 1. So if we take the log of it, it's always equal to 0. The Gaussian Copula, we're just going to take the log of the density and sum it up. And since this one has a parameter that we need to find, we are also going to use numerical optimization and find the best parameter. So I'm instantiating all of the samples here. And now we're just going to test which Copula fits the data the best. So this code computes the likelihood for each and also the AIC. And we can see that for the first samples, the samples from the Bivariate logistic, the best AIC is indeed of the Bi-Logistic. So if we would have if we didn't know that these samples indeed came from the Bi-Logistic, we would run over all the entire families that we could, and we would choose the best one. In this case, it would be the Bi-Logistic, and we would choose correctly. Of course, in real-world data, we don't have the ground truth. Here it's easier because we know where we sampled it from. And for the independence, we see that the lowest AIC is indeed the independent. The log likelihood is slightly higher for the Gaussian, but it's an independent Gaussian. So actually, because the correlation is almost 0. So the Gaussian has a parameter, and models with parameter will tend to overfit the data, even by a slight. Yeah, this is nothing, but still it has a better likelihood than the independence. Once you account for these extra parameters and you move to the AIC or the BIC, you get indeed that this model is not better than the independent model. And finally, for the Gaussian, we see that the best AIC, the lowest AIC, is indeed for the Gaussian. Now, instead of doing all the work we've done so far manually, we could have used the Copula library. And to sample, all we need to do is call the rCopula method and give it the Copula that we want to sample from. So here I'm sampling from a Clayton Copula with parameter 1. It's actually the same as the Bi-Logistic. And it's also the same as the AMH Copula with parameter 1. Here I'm sampling from the independent Copula, here from the normal Copula. And I'm specifying this parameter to be UN, where UN stands for unstructured. And that simply means that it will fit different rows for each pair of variables. Okay, so this is sampling. For fitting, what we can do is have a list of Copula families and then start by the Kendall's tau inversion trick, where we invert Kendall's tau to the parameter and then fit the Copula using maximum pseudo likelihood, starting with the parameter starting value being the one we found using Kendall's tau. Okay, so let's run this. And now we can apply this method to each one of these Copula and give it the samples. Here we'll give it the Bivariate logistic, and we'll order the results by the AIC. Okay, we got the results. The best AIC is the Clayton Copula with a parameter of nearly 1. So as we said, the Bi-Logistic is actually also the Clayton Copula with parameter 1. It's also the AMH Copula with parameter 1. We can see that their result is very similar, but we can see that there's like a large gap between them and all the rest of the Copulas that we've checked. So it does pretty well. We can also test for the 2D Gaussian. And here we see that indeed the normal Copula comes out with the best AIC and BIC and also log likelihood. I want to show you some more things we can do with the Copula library. For example, one thing we can do is define the copula with the marginals. So here I'm defining the copula, and I'm also giving it the marginals and the parameters for the marginals. And once we have this, we can sample from it. And this is how it would look like, okay? Another thing we can do is that instead of writing the density and the copula function, we can just define a copula and then look at the density and the distribution or probability function. And you can see that my method does exactly as well as the copula library method. Okay, so in the last video, I talked about higher dimensions, but I didn't mention the simple case. The simple case is when we have everything having the same dependent structure. For example, having a multi-dimension Gaussian. The dependent structure between each pair of variables will be a Gaussian copula, and we can have the same for other copulas as well. Here are the expression for the Gaussian copula CDF and PDF. Again, each pair of variables will have a Gaussian copula with its own correlation. But there's also a type of copulas, a copula's meta family if you wish, that is called the Archimedean copulas. For example, the Gumbel and the Clayton and the Bivariate logistics that we saw, they are all part of the Archimedean copulas. And the way they are structured is as a sum of generator functions, which are then inverted using the same function. So both the generator and inverse generator are decreasing functions. The generator maps the 0-1 range of the u's to the 0-infinity range, and the inverse does the opposite. And this ensures that the expression is indeed acting like a cumulative distribution function. Now, some call the inverse the generator and the generator the inverse. It doesn't really matter, but this is the Wikipedia representation. I think an example can help here. So for the Gumbel, this is the generator and its inverse. And so the d-dimension copula can be written like this. You can see that when we set some u's to be equal to 1, which is the limit in the u space, their term cancelled to 0, and what we are left with is the bivariate copula. Now, to sample directly from the Archimedean copulas, we use something called the Marshall-Olkin approach. And so the first thing we do is sample some quantity L from a distribution which is the Laplace transformation of the inverse generator function. Now, inverting the Laplace transformation can be difficult, but luckily we already know for each generator function or known generator function the associated Laplace transform distribution. And this distribution guarantees that the expected value of this expression of e to the power of minus L times t is equal to the inverse generator at point t. Okay, then we sample a bunch of standard uniform and we set the u's to be equal to this expression over here. We can verify that the joint distribution is indeed the Archimedean joint copula. We first look at the conditional distribution. Since the inverse generator is strictly decreasing, we get the inequality switches. Since the v's are IID, we get the joint conditional is equal to the product, and so we get this. And now, using basic rules of probability, the full joint is equal to the expected value of the conditional probability, that is to this. But by the definition of this distribution, we constructed this distribution such that the expected value of this quantity will be equal to the inverse generator function, and so we get that this is equal to this, and we proved what we wanted to prove. What about fitting copulas in high dimension? Well, in the simple case, it's quite straightforward. Since we know the density, we can simply check all the families, finding their best parameters, and then compare them using the AIC. So again, let's switch into R to see this. Okay, let's look at multi-dimension trivariate example, and let's take a simple distribution that is a simple copula where all the connections are the same, all the copulas are the same. In this case, I'm going to take a Clayton copula. The inverse generator is equal to this thing over here, and the Laplace transformation for this kind of inverse generator is actually a gamma distribution. It's already known. You can check it for yourself. You can take a gamma distribution, have the Laplace transformation on it, and see that you're getting this. And the parameters of the gamma are 1 over theta and 1. And so to implement this, I'm just creating a matrix to hold the values. I'm defining theta to be 5, for example. For each observation, I'm sampling an L value from the gamma. I'm sampling D uniform variables, and then I'm plugging minus log V divided by L into the inverse generator. Once I do this, I want to see it with normal marginals, so I'm just going to transform the u's to x's, and then I'm going to plot this. I'm going to plot the relation between x1, x2, x2 and x3, and x1 and x3. So let's run this. Okay, we can see that between every two variables, x1 and x2, x2 and x3, x1 and x3, the coordinates might change a bit, but the dependence structure is clearly a Clayton copula. And the reason I transform this to normal is because for me it's easier to identify the copula when you have normal marginals. And of course we didn't have to go through all this trouble. We could have just used the copula library, define a Clayton copula, give it the parameter, define the dimension, in this case to be 3, and then calling our copula on this copula, and it will give us the samples, and we would get exactly the same thing. Fitting high dimension copula, that is a simple copula, is pretty straightforward. We give it a list of candidates, we call fit copula, and we can apply this to all of the candidates, and we choose the best one. Okay, we see that indeed the best copula from all the families we gave it is the Clayton copula, and the parameter is very close to the true parameter, which is 5. Now, these simple high dimension copulas are nice, but they are quite restrictive. And VineCopulas, the ones I showed you in the last video, they are more versatile. So in the last video, we saw how we can decompose a joint density into a copula structure times the marginals. And again, this is only one possible structure. In the 3D case, there are 3 of these structures called vines, but the numbers grow very fast in higher dimensions. I want to elaborate a bit what is meant by the third C function. What we have here is actually a copula density function between two conditional values. This captures the dependence structure between x1 given x2 and x3 given x2. So to get the 3D copula density, we need to calculate the 3 copula densities plus 2 copula conditionals, or H functions. We can look at this from a generative perspective, and we can create a meta distribution where we define each one of these copula densities and also their marginals. For example, suppose we set the dependence between U1 and U2 to be a Gumbel-Copula with parameter 5, between U2 and U3 to be a Clayton with parameter 10, and between U1 given U2 and U3 given U2 to be Clayton with parameter 0.7. Now, we've set the copula between U1 and U3 given U2, but what about the unconditional copula between the two variables? Does it have a name? Well, not necessarily. It will often come out something that we don't really have a definition for, we don't really have a name for. It will be something that, some weird distribution function. Okay, fasten your seatbelts. Here's the hard part. How do we sample from a 3D vine structure? It's quite complex. For U1 and U2, we can use the same trick of conditional sampling that we saw before. That is, sample from the conditional using the inverse transform sampling. But now we also need U3 given U1 and U2. So we notice that this is equal to this, but we can decompose the density to this using the vine decomposition, and noticing that the C12 in the numerator and denominator will cancel out. If we replace this expression by W, we can write it like this. But we can also notice that this is simply the conditional, or H function, of the third copula. And one thing I want to stress out is that if we have a given copula, then its CDF, PDF, and conditional are all uniquely defined. So if we set a certain structure for the pink C13 given 2, we already have its h function. We can derive its h function. And let me remind you the nomenclature that we gave before. So when we are finding u2 given u1, we call u1 the condition value and s2 the target value. What we can do now is calculate the condition values v's, combine the v's with the uniform s3 targets, and invert the conditional of the third copula to get the w's. Okay, so here v is the condition value, s3 is the target value. Then what we can do is combine the u2's we already calculated and the w's we also already calculated to invert the conditional of 3 given 2 and get the u3's. Okay, so here u2 is the condition value and w is the target values, and then finally we get the u3's. Yes, I know, it's super complicated. I'm sorry, maybe there's a simpler way. If you find it, let me know about it. Okay, let's switch into R and see how this works. Okay, so sampling from VineCopula. We have that our first density is a Gumbel-5, the second density is a Clayton 10, and the third density, the condition density, is Clayton 0.7. So we need the h functions and the density functions of both Gumbel and Clayton. And this is exactly what I've calculated here. I won't go through the derivation. It's pretty tedious, but you can pause the video and verify for yourself that this is indeed the first derivative of this function, and this is the second derivative of this function, and likewise this is the first derivative of this function, and this is the second derivative of this function. So let's run this. And so now to compute the density, I compute the two h functions, and then I plug it in, I compute the first density times the second density times the third density, but not of just u1 and u3, of h12 and h32. And this is simply a vectorized version of this. So I'm gonna integrate over u2 in a second, and I want to be able to supply a vector of u2 to this function. Let's run this. Okay, so now what I want to do is calculate the joint for u1 and u3. And to do this, we need to integrate out u2. So the method is quite simple. I'm taking a grid of points over u2, calculating the density in each of these points, and then sum them up. But there's a bit of a fancier way to do this with Legendre polynomials, so I'm just going to use that. It's not that much of a difference, but this is what I'm going to do. And so to calculate the joint of 1 and 3 with normal marginals, because it's easier for me to view things in the normal space, I'm going to calculate the u1 and u3, calculate the density of 1 and 3, the copula density between 1 and 3, and then multiply the three of them to get the density, the joint density of 1 and 3. I'm going to expand the grid, and I'm going to calculate this function for each point of the grid. And this is the joint density between x1 and x3. So this is not a known copula family that I know of. It's just something that arises from this Vine structure. So when you give x1 and x2 this copula, and x2 and x3 this copula, and x1 given x2 and x3 given x2 this copula, this is the joint distribution between x1 and x3. Okay, so for sampling from the VineCopula, I've mentioned that we have to use the inverse conditional method. I don't want to calculate this by hand, so I just have this function where I give it the conditional and it's already inverting it using the uniroot method, and I also have a vectorized version of this, so I'm just going to run this. And now we are going to do the algorithm that I've just described for you. I'm going to sample S1, S2, and S3. I'm going to set U1 to be equal to S1. I'm going to set U2 to be the inverted of the conditional, and the conditional is the conditional of the Gumbel, and I'm giving it U1 and S2, and it will find the U2 for me. Then I'm going to compute the V's. The V's are simply the conditional Gumbel distribution using U1 and U2. Yeah, so actually here it's u1 given u2. Yeah, so you first, the way I made this function is that you first give the condition value. Okay, then we invert the Clayton, yeah? So the third function, the h function of the third density, the conditional, we invert it to get the w's. And notice that the targets here are S3 and the condition values are the v's. And then once we have the w's, we make the w's the target, u2 the conditioned values, and we invert the conditional of C3 too, and so it's also a Clayton, and we get the U3. Finally, we bind all these together, and just for us to visualize it, we transform it using the standard normal. Okay, so in case we didn't run this, let's run this. And now we can again view x1, x2, x2, x3, and x1 and x3, this time with the points themselves and the empirical contour lines. Okay, so we see that the first copula indeed looks like a Gumbel-Copula, okay? The second one indeed looks like a Clayton copula, and the third one indeed looks like our undefined copula that arose from having this structure. Let's visually try to see the difference between simple copulas and VineCopulas. So in simple copula, we have straight dependent structure between each two variables, and they are all the same. So u1 and u2 is the same as u2 and u3, is the same as u3 and u4, it's the same as u1 and u4, u2 and u4, u1 and u3, etc. And each line, it represents here a Gauss copula, a Gumbel-Copula, etc. But in VineCopulas, we specify dependence between a set of variables according to the specific vine we use to decompose the joint distribution. So if we used a d-vine, a drawable vine, we will get this on the left. And if we use a c-vine, we'll get this on the right. And each edge now can have its own different copula. It doesn't have to be the same. So the edge connecting 1 and 2 can be a Gaussian, and the edge connecting 2 and 3 can be a Clayton. And each one of these connections, these connections between 1, 2, 3, and 4, for example, in the d-Copula, is called a tree. And we will always have d-1 trees. Okay, so if we have, here we have 4 dimensions, we have 3 trees. One tree is for the direct connections. The second tree is for the connections given one variable. The next tree is for the connections given 2 variables, etc. And so d-vine and c-vines are 2 special structures from the more general set of regular vines. But in all types of vines, there's the different trees, and each tree has to be a minimal spanning tree. That is, you can only have one root from each node to another node. So in the case of the d-vine here, there's only one root from node 1 to node 3. There's not other routes that you can take. But if, for example, I were to draw a line directly from 1 to 3, then this would break this assumption. It will create a loop, it will create a cycle, and this is no longer true to the decomposition we've derived before. And so how do you fit a VineCopula? We saw that simple copula is rather easy to fit. A VineCopula is a bit trickier. If we already know the structure, then it gets easier. We simply fit each connection separately, choosing the best family and finding the best parameters. But what happens if we don't know the structure? Well, we first need to decide on the structure, on the vine, on the decomposition. And the way this is usually done is using greedy algorithms. So we fit each tree using a greedy algorithm that maximizes some edge weights, like connection weights. And usually the weights that we are using is the absolute value of Kendel's tau. Once we find the structure, we fit each connection and we move to the next tree. And here is a small demonstration of the 2 main greedy algorithms that can be used, taken from Wikipedia. The first is called Prim's algorithm, and it finds the best connection between any 2 nodes, and then it tries to find the next best connection that can connect to any one of these 2 nodes. And after that, it continues, it always tries to find the next best connection to any one node from the set of nodes that are not yet connected. And so here, we always accept a connection. So we can try different connections, we can look at the best connection, and we always accept it. Compares this with the Kruskal algorithm. Here it connects any two nodes with the best weight. And so here, some connections might not be valid because it will break the minimal spanning tree criteria. So you can see now it just rejected a connection because there's already a path, there's already a route between the two nodes. So these are rather simple algorithms, but since they are greedy, there's no guarantee that we actually arrive at the global optimum. And this is a bit complex. I'm not going to manually implement this, but luckily we have a library that can help us out. It's called VineCopula, and we can use it either for sampling or generating data. We need to specify the vine structure and the copula for the edges, so both the families of the copulas and their parameters. And for fitting, we can either supply the structure in advance or let it find the best structure using a greedy algorithm. Let's see this in R. So we're calling the VineCopula, and in 3D, we will have 3 pairs of copulas, but in higher dimensions, we will have more pairs. And what I mean by pair is not the number of decompositions, this is much greater. What I mean by pair is how many connections there are between nodes. How many edges are there in all the trees, in all the levels of the trees. So in 3D, we have the first tree is combining 1 and 2 and combining 2 and 3, and the second tree combining 1 and 3 given 2. So for D vines and C vines, we specify an order, and we specify the families of each one of these connections. So there's different encoding. 0 is independent, 1 is Gaussian, 2 is T, 3 is Clayton, 4 is Gumbel, 5 is Frank, and it goes on. We set up the parameters for each one of these families. We don't have a second parameter, so we can leave it 0. We feed it into the drawable to rvine function to get a regular vine function that is actually a d-vine. And you can see it tells you that between 1 and 2 it's Gumbel, between 2 and 3 it's Clayton, and 1 and 3 given 2 is also Clayton. Okay, we could have also done this in a c-vine manner, and here you can see 1, 2 Gumbel, 1, 3 Gumbel, and 2, 3 Gumbel. This is just because I chose Gumbel for the entire structure. And we can simply simulate from it. We call the rvine sim function. We give it the structure and the number of samples, and we sample from it. Again, I'm transforming it to standard normal. And again, we get the exact same plots as before, only here it was done automatically. We didn't have to work so hard and sweat. And indeed, the first one looks like a Gumbel, the second one looks like a Clayton, and the third one is this unidentified new distribution. Here's a 4-dimension example. So in 4-dimension, we will have 6 pair of copulas. We'll just do a d-vine here. I'm giving the first one to be a Gaussian, 1, 2 to be a Gaussian, 2, 3 to be a Clayton, 3, 4 to be a Gumbel, this to also be a Clayton, this to also be a Gumbel, and this to also be a Gaussian. These are the parameters for all of these copulas, and then I just create the copula. I sample from it, and you can see I'm plotting here just x1, x2, x2, x3, and x3, and x4. I'm not plotting any of the other ones. Okay, so the first one looks like a Gaussian, second one looks like a Clayton, third one looks like a Gumbel. So looks good so far. What about fitting the copula? Well, if we know the structure or we have some idea about the structure, we can give the structure to the fitting function and then tell it what family should it look at. And if we run this, we see that it found the best fit for the 1, 2 to be a Gaussian, to the 2, 3 to be a Clayton, to the 3, 4 to be a Gumbel. The parameters are very close to the true parameters. In the second one, it found 1, 3 to be a Clayton with the right parameter, 2, 4 to be a Gumbel with the right parameter, and the 1, 4 given 2, 3 to be a Gaussian. So it did a really good job once we gave it the structure. What happens if we don't give it the structure? So what happens if we just tell it, hey, find the best structure, and these are the possible families, couple of families for each connection, for each edge. So here we see it gives something completely different. So the 1, 2, it's said to be a Gaussian. It didn't connect 2 and 3. Instead, it connected 4 and 1 and 4 and 3. So it's a regular vine. It's not a D-vine. It's not a C-vine. And it chose different families. For example, here it chose, I think 5 is Frank. I'm not sure. Here it chose some other one, 14. I think maybe it's a rotated Gumbel. Here 33. I have no idea what it is. Okay, and here are the parameters for the different connections. But we see, oh, it says it is a D-vine. How come it's a D-vine? 1, 2. Oh, actually it is a D-vine. It's just a D-vine that starts from 3 to 4, 4 to 1, and 1 to 2. So it is a D-vine, just in a different order. But we see this is not very good. I mean, it's not the actual distribution that the data came from. Maybe it's a close enough distribution. I don't know. I mean, we can try to simulate data from this structure and see if it resembles the data that we gave it. But bottom line, it's not guaranteed to find the correct synthetic data. Hopefully it's good enough. What we can also do is use the bi-cop select between any pair of variables and give it the family set, like which candidates to look from. And this does a pretty good job, and also pretty quickly, much quicker than the Copula version. I don't know if it's cutting corners or it's just a better implementation, but it did it really fast and it found the correct parameters. So yeah, good job. Finally, just out of curiosity, let's see what it does if I give it a simple high dimension Copula. So here I have a Gumbel-Copula, not a Clayton Copula, with some parameter that I forgot. And I think this is 4 dimensions. And I'm telling it to find the best vine structure. Now, it wasn't created using a vine structure, and I'm not sure what is the vine structure of this distribution, but let's see what it finds. So indeed, between 2, 4, 4, 1, and 2, 3, it says that everything is Gumbel, but when it looks on the conditional copulas, it says it's Clayton. Could be, I don't know if it's true or not, but it's interesting that it did find for the unconditional that it is Gumbel. So it did a good job, at least in that part. Well guys, it's been long, I know, but I hope it was also worthwhile. I think you understand copulas much better now, and hopefully you also have more confidence about them and about how to use them. That's all for this video. See you in the next one.